All right. In this part, in the second part, we will look at how to implement Kruskal algorithm. Okay. So the idea is that you will need to read some input and then sort edges, and then try to add edges in the increasing order of weights, and then we need to check if the new edge that we're looking at is gonna create a new cycle or not, okay. And we use the union file data structure for that. All right. Okay, so let's look at the task that we need to do. Okay, so there's task called MST1, which I have I hide it because it only have a small number of vertices, but we work with 100,000 vertices here. Okay, so the input is a graph with n vertices and m edges. Okay, the input, the first line of the input, you need to you should read the task statement. So, the first line contain n and m, and then these are m edges. The first number is the first two number is the two n nodes of the edge, and then this is the weight. Okay, so we start by reading the input. We'll see that when we only want to compute the minimum spanning tree, we don't need to use the adjacency list. We can just keep the list of edges. But if you want to do something fancy with the tree later on, maybe you need to use the adjacency list for keeping the graph. But here, we just need to maintain a list of edges. Okay. All right, so let's try to implement it. Let's read some input. Okay, so let's see how we're gonna keep the thing. So we need n and m, right? And then we need a list of edges. So let's say max m is 200,000. Max n, probably not. I'm not gonna use it probably, but let's say keep it. And then we're gonna we need to keep two endpoints. So we can do this something like max m, and we have an array of two, one for the two endpoints, and then we need to keep the weights of the edges. So that's probably the stuff that we need to keep. All right, so we just read n and m, and then look at each edge, right? A, B, and W, right? Okay, and then we need to make sure that the edges, the vertices number start with 0, so that we good with it. Okay, and then we need to keep edges I. The first one will be A. This I, the second one, and then we need to keep the weights of the I as W. Okay, so that's the input that we need, and then when we want to run the minimum spanning tree. Okay, so and then we have the main function here. We input, and then we do something. When we want to compute the MST, again, we need to sort the edges, right? So we somehow need to use this first, and then we need to use algorithm, so that we need the sorting subroutine. Okay, we want to sort the edges by the weights, right? So we need some vector. We need to keep the pair of the weights and the edge index. So basically, we need something like vector pair of int. Okay, this is just for sorting. Let's call it the view weight edge, something like that. And then we say push back, make pair. So we need to put the weights first, and then we need to put the edge index there. Okay, so these vectors we will sort the edges using this vector. So basically, the first step of the MST is called sort. Now, this weighted edges, let's call it sorted edge. That's look better, right? Okay, so sorted edges. Let's call that. Okay. Now we have these vectors. The first element is the weight, and the second one is the indices of the edge. Okay. Now we can just go through them. Okay. Okay, and then the edge that we're looking at is the sorted edges I and the second. So that's the index of the edge that we are looking at. Okay, and then this edge has the first endpoint is U, the is edge, right? And then the weight. That's the weight. All right. So now this is the edge that we are looking at. We want to make sure that so we need to check if U and V belongs to the same component, right? We need some data structure for that. That would be the union phi data structure we use. And then so if something in the different components, okay, and then if that's the case, we need to compute the weight, MST weight, and we need to return that, right? So the weight is 1,000, and there are at most 100,000 edges. So you can keep it as an int. Okay. So if that's the case, then we need to add e to the tree. So basically, we need to count the weights and then update the data structure. Okay, so that's the whole thing. Okay, how can we check if U and V belong to the different components? So we use union phi. So we call phi U and phi V. Okay, so if U and V belongs to different component, the ID that return from the find procedure would be different. Okay, so that's the thing, and then we add e to the tree. So we basically want to compute the weights, not the tree itself. If you need to compute the tree, if you need to store the tree, you need to somehow to keep the edges. Okay, so but here we just need to keep the weight. So we say weight add with W or weight. Right, and then we need to update the data structure, so they belong to the different components, so we just call union. Okay, but union is a keyword in C++, so we gonna rename the procedure called union sets, and then UV. So that's the result. Okay, but typically when we call find, when we do the union sets, we can, okay, this is the roughly the code, okay, and then we need to implement find and union set. Okay, all right. In our procedure, when we call union set, we typically want to pass the set ID to the union procedure instead of the element U and V itself. So somehow we would rewrite the whole thing like this. We call PU as find U, and then PV as. The reason I use P is I will explain later on, but this is like the parent of U, something like that. Okay, and then equal to PV. Okay. If they belong to different set, we do that, and then we call union set of PU and PV. So when we call union, we basically give the set number to the function union. Okay, and after that, everything should work. Okay, all right. So let's try to implement the union file procedure in a way that is not efficient, but it should work. All right. Okay, so let's do that. So before we start, we should initialize init union file. Okay, we should initialize it first, and then we call file, and then we call union here. All right. Okay, so let's try to implement the union file data structure so that we can submit this with a working union file data structure, but with a very slow implementation. Okay. All right. So the simplest way to keep the union file data structure is to just for each set we keep the set number. Okay, for each element we keep the set number that this element belong to. So let's make a data structure here. Set number, let's call it set number max n. Okay, this is the number, the set number of the elements. Let's call set numbers. Okay, when we call init union file, we basically assign each element a different set number. So we basically do this. So we say set numbers of I is going to be equal to I. So that's the easiest way to do that. Okay, and when we call file, we just return set numbers of u. Okay, so this is something like if you want to know the set that this element belong to, so we just keep the set index here. Okay, when we talk about implementation of union file, we'll see more of that, but the idea is like this. And then when you want a union set, okay, so this is a set number, right? Let's call pu and pv. Okay, we just need to we want a union set pu and pv, right? So we can rename everything that has the index of pv to pu. That's it. So that's the way to union it. It will be very slow, but it should work. So if set number of I equals pu, then I say set numbers I equal pv. Okay, so that's it. You can either change every pu to pv, or you can change every pv to pu. Okay, but I'll do it this way. Okay, so this is the simple union file data structure that I have. Maybe you should pause a little bit to figure out what it is and see if it works as I claim. So basically, file would return the set number. Given one element, it returns the index of the set that this element belongs to. Initially, everyone belongs to its own set. So the set number for element I is just I. Okay, and if initially everyone belongs to different set, when you call union set, we basically rename everyone who belongs to set pu to set pv. Okay, so now if you ask find again, it will be on a different set. All right, so this should work, but it will be really slow. So let's try to compile it. Oh, okay. MST should return the weight. Okay, and also main should return 0, and then cout MST. Just print the weight out. Okay, so let's try with the sample input here. Okay, see 22. No, that's correct. So it should work. So let's try to submit the whole thing. Okay, let's see. It should give you about like 50% because it is very slow, I think. And everyone submit at the same time it will be very slow. So you give you like 25 points because it's very slow. The other cases is large one. Okay. Okay, but it's correct, but it's really slow. Okay. Now you need a better way to implement this union file data structure. Okay, that we'll discuss next. All right, so let's see the previous representation in pictures. So we keep set number as an array like this. So suppose these are our sets. So suppose we have these 4 sets. The representation that we get is probably something like, you can see that the element belonging to the same set has the same set numbers. So when we say find, let's say find 2, it will return 5. Okay, and then if you say find 5, it will return 5. Okay, now if we would like to union, say these 2 sets, say 2, 3, 5 with this set. Okay, suppose we want to make them the same set. We need to change either from set number 5 to set number 6 or set number 6 to set number 5. So the subroutine for union would basically suppose we want to change 6 to 5. This is what we'll do. Okay, and you can see that it takes time, linear time, to do the union. Find is really fast because you just look up this array and answer. So find run in O1, but union run in ON. And if you have many unions, then it's become really slow. Okay, so this is the previous representation of our sets. So let's see the improved one. Okay, so the improved one, we basically try to maintain the set structure as a tree. Okay, in the beginning we say every node is a set of its own, right? So it's become the root of the tree. Okay, I'll show you by example. So everyone just keep the pointer to the parents, but if you have root, you have a pointer to yourself, like that. So the pointer is basically you keep the number. So everyone in the beginning, everyone just keep its own number. So you can think of as the parent pointer. So this is called parents. Okay, so the parent pointers would point to itself. That's how you know that you're at the root. Okay, like this. Okay, but to make the illustration clear, I would remove this kind of arrows. Okay, now suppose I would like to union 0 and 2. Okay, so I need to combine them into the same tree. So I can either maybe do this. So I change the parent pointer of 2 to 1. So instead of pointing to itself like this, I said point to 0 like this. In this case, when I call find at 0, I get 0. When I call find at 2, I need to traverse all the parent pointers and return the root of the tree. Okay, so in this case, in our representation, I would put a 0 here. Okay, so from 2 to 0, so I get that's it belong to the same set. So let's see a few more example. So suppose I want to union 3 and 4. I would somehow pick one of the node, and then I update the parent pointers to this. So 3, this would be 4, like that. Now suppose I would like to union this set, okay, this set and 5. Okay, there are 2 ways that I can do it. Okay, one is that I would update the pointer of 5 to point to 4, like this, or I can update the pointer of 4 to point to 5. Okay, this will have the same effects at the end, but you can see which one seems to be better. So if I update by changing the pointer of 5 to 4, then when I call find 3 or find 4 or find 5, it will return 4, right? But on the other hand, if I do something in reverse, I just point 4 to 5 like that. When I call find 3 or find 4 by 5, the result would be 5. Okay, So let's do it like this so that it looks really bad. So I need to only update the pointer of at the top. Okay, to 5 like that. Pointer at 3 that would go to 4. I would keep it like that. When I call find, say find 3, it looks at it knows that it's not the root, so it's asked to find the root of the its parent and so on. So when I call 5 3, it in turn call 5 4, then 5 4 call 5 5, and 5 know that it's itself it's the root, so it return the value 5, so you get 5 3 to be 5 5, and so on like that. So the pseudocode, given this representation, the pseudocode for 5 would look like. So let's do one more union, maybe 2 more unions. Okay, suppose I want a union 6 and 7. I might do something like this, 7 to 6. So I update this. And if I union 6 and so let's say I want to union the set containing 5 and 7. So first I find the root. So I traverse the parent pointer to see 5 and 6, and I pick one to be to change. I change the parent pointer of one of them. Maybe I change this one. Okay. Or let's say let me change. The tree will be really long, really deep. Okay. Okay. Like that. So I update the parent pointers to 6 like that. Now when I call find 3 4 5, it will return 6. Okay. When I call find 7, it also returns 6. So this is the parent pointer representation of the set. Okay. When you call find, the pseudocode for 5 would look like this. If parent u equals to u, then return u. Otherwise, else you just return. You recursively find the root of the parents of u. Okay. So with this representation, the ID of a set is the node number of the root, basically. Okay. When you call union, if you know that u and v is the root itself, you just update the parent pointer of one of them. But if you're not sure, you can just call this u equal to find, u and v equal to find v, and then you update the parent pointer, say parents u equals v, something like that. But you need to make sure that they're not in the same root. If you have the same root, then it would be crazy to do that. It won't becomes a bug, I think, but let's make sure. If u is not equal to v, then do this. Okay. With this representation, the running time remains the same, because you can have from this example you can see that when you call find, it takes quite some time, right, to reach the root, and you can also have a sequence of node unions that create a list of parents that look like this, that can be really far. Okay, can be very far. So when you call find, it takes maybe it may take n time, but union is really fast because you can just take the parents and update, assuming that u and v is also the root. Okay, so find can be really slow, n, but union can be much faster. Union is O1. Okay, but we introduce a simple technique that make sure that find is gonna be O log n. Okay, by doing a more careful union. Okay, so let's look at the idea first. You can see from this example. Okay, before you call union 5 and 6, when you want to call union 5 and 6, you know that 5 is somewhat larger than 6, right? So instead of changing a pointer of 5 to 6, instead of doing this, right, you should do something else. You should do the reverse. So you should update the pointer of u to 5 itself. Okay, so don't just arbitrarily update the parent of one guy to the other, but you want to make sure that you update the parent so that the tree is not too deep. Okay, so one way to do that is to keep one more information. Okay, so let's do that. Okay, so we're gonna keep something called ranks. Initially, the rank of everyone is gonna be 0, and when you do your union, okay, you want to make sure that if the two nodes has different rank, you always point the one with lower rank to the one with the higher rank. The idea is like the rank basically represent how big the tree is. So suppose you want to union to these two guy, U and V, and if U is larger, maybe deeper, you better point V to U, right? This would basically keep the depth logarithmic. Okay, I think in the class, the instructor of algorithms class should give you some analysis, but the idea is that every time you point to someone else, that your tree go larger by a factor of 2. So the tree can double the size by at most n times before you reach the number of nodes to be n. Okay, so we keep the rank pointers. Okay, the 5 procedure run in the same way. Okay, and the union, we want to make sure that so let's update the union code a little bit to reflect this choice. So let me do this. So if U equals V, then I just return. Otherwise, I would try to join the one with the lower rank to the higher one. So let's say if rank of U is less than rank of V. If U is less than V, so basically I would just say I would change the pointer of U to V. So parent of U equals to V. Otherwise, I would do the opposite. So I would basically say parent of V to be U. Okay, I update the parent pointer of V. But not only that, so if the rank of U are the same, if the rank are not the same, I point the one with lower rank to the higher one. So but if they are the same, so if they're the same, if rank, otherwise you will always get rank 0, right? Equals rank V. If they're the same, I point V to U, so I should increase rank of U by 1. Okay, so this is my code. So we basically update the parent pointer to point to the one of the higher rank. But if the rank are the same, in this case, like rank U is equal to rank V, and I point V to U, right? So I do this, I point V to U. So I increase the rank of U because it gets larger. Okay, so this is the pseudocode. By doing this, you make sure that the depth of the tree is locked in. Okay, so you can do union in the O1, assuming you have find the root of that. So and union runs in O1 because it's just if, simple if. But with this, you ensure that the tree depth is at most log n. So 5 procedure run in log n time, and that's really fast. Okay. Finally, there is another kind of update. Okay, although you can have you make sure that your tree is like the depth is log n. You can also do some more optimization. Say you want to do 5U and you traverse the tree like that to find. So maybe there's some other nodes like that. But you start with U and then you follow the parent pointers like this to the root, right? And you figure out the root there. But then you have already find the root. So next time maybe you can save the traveling like that by change the root of everyone along the way to the root itself. So this would basically shortcut the next time you do the find, when you call find, you get to the root instantly. Okay, so this is called path compression. Okay, you can change the code for that simply like this. You just save the solution, p equal 5, and then you update parent u to p, and then you return p. Okay. So with this is called path compression. It will make the data structure even more, faster than the previous one. The total running time will be like close to constant. We're not going to analyze it here, but this is what people do. Okay. So this is the union file data structure in on paper. Next, we'll see how to implement that in your code. Okay. So basically, 3 ideas. First, let's use parent pointers to keep the tree. Okay. It will give you the workable, usable data structure, but it will be really slow. And then you have ranks. Okay. You ensure that you do union by rank. You point someone with lower rank to the higher one to make sure that the depth is not too high. It will ensure that the depth of the tree will be locked in. Okay. And finally, you can do path compression, which even make the data structure run faster. Okay. So three key ideas, and we'll see how to implement that in your code. All right. So we use the procedure that as described previously. So we will implement the first with we'll change the set number to a parent pointer first. Okay. So let's call it parents. Okay. And initially everyone is the parents of itself. When you do the find, so you check if the parents, if u is the parent of itself. If that's the case, then just return u. Else we just recursively call find of parents u. So we if u is parent, is the root of the tree. We call the tree that we've drawn previously, right? Then we just return u. Otherwise, we just recursively ask who is the root of the parents of u. Okay, so that's the file procedure. And when we want to do a union, okay, if we just do some basic thing, we need to ensure first that u and v are the roots of their own tree, right? I'm not gonna check it, but if you miss this, your code might screw it up. Okay, you can check if it's if parent. So I'm not so let's check it for now. If parents pu not equal to pu, we just say pu equals find pu. Okay, so to make sure that we're not gonna screw it up. Okay, and if pv is not root of pv, we just update find pv. Okay, this will ensure that even though if we don't really check that, it should be fine. Okay, and if pu equals pv, that means u and v belong to the same set. We just do nothing, we just return. Okay, and if we just want to join the root, we can just do this parents of pu to be pv. So this is like we set we point pv pu to the pv. It become the root, the child of pv. But this won't give us the an efficient implementation of the code union file, but it should work. So let's see if it works. Oh, sorry, I missed it. Okay. All right, it's correct now, but it's slow. It's still slow because there can be a long path as we discussed previously, right? So we need to do first optimization that we use is to do the union by rank. Okay, so we have another variable called rank, and we say rank I equal to be initially they are all 0. Okay, rank be 0, and then when we want to do the union, we check, right, if rank pu is larger than rank, if rank pv is larger than rank PU, then I'm done, right? I just point PU to PV. Okay. Otherwise, I would point PV to PU. Okay. PV to PU. Okay. But if they have the same rank, okay. So if they have the same rank, then I need to increase the rank of PU by 1. So if rank of PV equals rank of PU, in this case, I point PV to PU, right? Okay, so if that's the case, then I say rank PU plus plus, okay? Okay, so that's the union by rank. Let's see if it works. Oh, okay, so C++ has the variable function called rank already, so let's call it ranks. So we have many ranks. Okay, let's do that. Okay, let's try it again. Let's see if it works. It works. So let's try to submit the whole thing again. It should pass. Now it's really fast now, I think. Okay. But you can further optimize the whole thing using path compression. So union by rank ensure that every tree, the depth of every tree is log n. So the running time of this is going to be m log n. So it's really fast now. But you can do even more improvement by doing the path compression. So when you do the find, you make sure that when you get the result, you update your parent. Okay. So if parent is you just return. Otherwise, you say result, right? P be the result by parent, and then you update parents of you to be P, and then you just return P. So basically that. Okay. So you change the parent of everyone to the result. This is called path compression. So as we discussed previously, so okay, we can change that. The running time will be faster. So let's take a look at the current running time that we have. This is MST2. Right? If you look at your submissions, this one, you can see the running time is this 0.128. The one with timeout is like 2 seconds, right? So this one is faster. Okay, 1.2. Yeah. So let's see the next one, the new one. So let's take the faster one. Okay. It might not be noticeably faster because the running time is slow because of the 1.6. Oh, okay, slower. Let's see, slower because it's a little bit slower because the running time is dominated with the IO, I think, the read input. So let me try to use fast IO so that you can see the different. All right. Okay, so let me try to add this. Okay, so let's do this first. This should be the faster code, faster one, the one with the path compression. So let's see if actually faster. But input is really small, so you might not notice the. Okay, so let's see. Selected 1.04. Okay, so and let's look at the one without the path compression. So let me remove the path compression part here. Just remove this. Okay, let's submit again. So this one is the path compression. This is a recent one. Slightly faster. Okay, 112. It's like 14114. Okay. If the input is larger, it should be a little bit faster, but not that fast. Okay, because running time it depends on something else. But usually with path compression, it will be faster. Okay. This one doesn't use path compression. Okay. If n is really large, the improvement might be noticeable. All right. Okay. Now that you have a union file data structure here, I'm gonna provide you with the code. Let's look at the tasks that you have to do. The first one is milk bubbles. This is basically the data. It asks you to implement a union file data structure. It doesn't ask you to implement minimum spanning tree at all. So you need to take out the union file data structure from the code that we have and try to implement it so that you can complete this task. The other tasks that we will work on will pretty much be related to minimum spanning tree and the task heavy cycles here. So this task is related to the Kruskal algorithm, but you need to work with the tree itself as well. So so this is like optional, but it should help you to understand the algorithm a little bit better. All right. So there might be some other optional tasks or tasks for you, but roughly all this will be related to minimum spanning tree. All right. Okay. Have fun.